Yeah, here we are in OR, and I have put this code file, image denoise, up on Blackboard, so it should be available there for you now. And the image that we're going to use, so it's stored actually in a text file because it's just a binary image. There's some wonderful packages in OR to look at image analysis. One of them is called Image OR. Um, and that's great, so that can kind of load images and plot them and all the rest. Lots of functionalities there. We're just going to keep it simple for now. And what we'll do is we're going to use this capital M matrix library mainly for plotting. It does really nice image plots of matrices. um, our image file is a very appropriately named perfect example. Meow. And we are so what we're going to do is read that in from the text file, convert it into a matrix, and then visualize it, right? So we'll see what that looks like. So let me just now, so within the matrix library, read in the image file. So just to have a quick look at that image file and see what it looks like, right? So there's like tons and tons of zeros, as you can see. And then where we have patches of, I'd see some patches of ones there. Yes, so the ones there, they're starting to show the outline of the proud puss in the picture, right? So you can see that the pattern is not solid, right? So there's kind of one surrounded by zero. So this is probably like a strand of hair from the Persian quote. Okay, so let's just have a look, see what that image looks like. So we'll convert it into a matrix. So read.csv, by default it reads things in as data frames. Data frame is like a list. It's not a matrix, so a matrix will have every column with the same data type. Data frame allows columns to have different data types. So what we'll do is convert it to a matrix. Take the dimensions of that to tell us how many pixels are in the rows and the columns. Take the product of those to tell us how many pixels there are in total, and then visualize the cat, right? So what this is doing here is just literally plotting our ones and zeros, right? So it's putting a dark square where there's a 1 and a white square where there's zeros. Now the next thing we want to do is to make this a noisy image, and we said that we were going to flip the pixel values with probability 0.1. So what we do is we create a vector of flip values, right? The vector is going to be, it's going to have a length which is the number of pixels in the image, and which is by so it's like 98,820, so nearly 99,000. So it's going to create a vector of size roughly 99,000, which tells us whether the pixel is going to be flipped or not, right? And they're generated independently, so it's an indicator to tell us whether the pixel should be flipped or not. And then we'll convert that into a matrix, reshape it into a matrix, and then we form the noisy image by doing a kind of a matrix addition and element-wise multiplication. So if flip is an indicator that the image is flipped, then 1 minus flip will be an indicator of when we're not flipped, right? So we take 1 minus flip times the IM, which is our binary matrix giving us the image, and then flip times 1 minus IM. So 1 minus IM here would be the flipped image. Right, so let's just see what that looks like. So we'll store that in noisy.im, and then that's what the noisy image looks like. Of course, if we increase the probability of flipping here, right, to 0.3, we'll get an even noisier image, right? So you can kind of play around a little bit with this here. So by 0.5 we should basically lose all kind of signal there, so we can't discern a cat because we flip everything. So this is really interesting for kind of you know, thinking about how noisy signals can be and what chance we have to reconstruct them actually. So now let's just leave it at 0.1, right? We'll have an easy day today. Okay, so we won't, of course, the problem, so just on that note, right, so the problem is obviously going to become more challenging, right? So if we set this at 0.2 and the image becomes noisier, then it's harder for us to discern the outline of the cat in that case. So the problem becomes more difficult the higher that theta is, the more disturbance there is in the image. Right, okay. Now, so what we're going to do is imagine that this this picture, so we have, you know, 366 pixels along rows, 270 along columns. So we're going to imagine it as a 366 by 270 regular lattice, and each site on the lattice corresponds to a pixel in the image. So we'll call in our lattice utils and then build up the neighborhood structure of that as we have before. Extract the list of neighbors. What we'll begin by doing is so beta is a parameter that we have to choose. So this is our auto logistic parameter, which describes the correlation we have with our neighbors, or the correlation a specific pixel or site in the lattice has with its neighbors. We'll just look at a strong correlation to begin with. So we'll take beta equal to 4, and we'll again use this constraint on the alphas, that the alpha is equal to -2 beta. So we talked about that previously as well. So just kind of flip back if you don't know what I'm talking about there. All right, so now I think what I've done is I have defined theta twice, but that's okay. Don't shoot me, okay? That's we can work with that. It's not a crime. And we have, so when we looked at the full conditional, so if you just have your sheet of paper in front of you there, when we looked at the full conditional, we saw that there was this expression, this log theta over 1 minus theta, that appeared kind of every time we wanted to do a full conditional. And so what we'll do is we'll pre-compute that, okay, because that takes, you know, so 1, 2, you know, 3 or more floating point operations each time we want to compute it. So what we'll do is we'll pre-compute that quantity so we can use it just again and again every time we're doing a full conditional. This is a kind of an advisable thing to do if you have a kind of a lot of these quantities that need to be computed again and again. And okay, so the LOs, that's right, that's okay. And then the next thing is to actually frame this as the statistical problem that we formulated. So we want to make a vector which has length, which is the number of pixels in the image, and that's going to be our noisy image. So we want to vectorize this noisy image and store it in a vector called y. And then we have the true image that we want to recover, and that's going to be in a vector called x. What we do is we initialize x, and then we run through our sampling algorithm, our Gibbs sampling, updating the sites in each sweep of the algorithm. So we initialize that x as if we're just flipping a coin at each pixel in the image. Now what I want to do is at the end of this, so I'm going to run a kind of a Gibbs sampler, a chain, and then at the end I want to summarize the output. So I'm going to iterate it, you know, 500 times in this case, and I want to summarize the output at the end. What I'm going to do is to get a kind of an estimated image, I'm going to take the modal pixel value for each site in that lattice, and that's going to become my kind of estimate of the pixel at that point. And so what I'm doing here is I'm just storing the results of the runs. Now let me just describe here the MCMC, or the Gibbs sampling algorithm in here. Right, so, oh dear, apologies. So we're going to iterate through through 500 sweeps this algorithm. In each sweep of the algorithm, we cycle through each of the sites and update their value from their full conditionals, based on now the observation of the pixel in the noisy image and its neighbors in the true image that we've got so far. So that's what this part of the algorithm is doing, right? So this loop here, and what we do is we just kind of randomly shuffle the order that we visit the nodes, and then we go in. Everything here is very, very similar to when we were generating samples from the auto-logistic model. The only modification is in forming this linear predictor, this eta I, and we just add an extra term there, and that extra term is to do with the this kind of log odds thing, and the value of the pixel in the noisy image. So we cycle through that lots of times. We update our storage, so this is to compile our final image at the end. And what we do here is well, we print out a little progress update. Might be a little bit slow, but what we'll do is on each iteration we're actually going to replot the image, right? So it'll show us as the sampler progresses how we're doing at denoising the image. All right, so let's take a look at that now. Okay, now prepare to be dazzled or not. Okay, so there we start with the noisy image, and then we carry on sampling here. So we're obviously updating at each point. You can see that we have some, well, you might be able to see if you have really good eyesight, some pixels in the bright areas that are still dark, and they're kind of being sampled randomly. So what we're seeing here is the work of the full conditionals, this random sampling. But we can see that we sort of converge on the shape of the cat fairly quickly. And yeah, so I took a little bit of a break there while this was running. And if you have the patience, run for 500 iterations. Of course, much faster ways to do this, but this is just for illustration here. And what we'll do now is we'll take the modal value at each pixel. So we'll see, what at each pixel, so each kind of point in the lattice, or each site, what do we visit most often, 0 or 1, and then we can construct a map image of the cat. So this is our estimated reconstruction of the original image, and we can see that it does a pretty good job, right? But what we do notice is that if we have a look at the original image, we can see that we sort of see a little bit of degradation, right? So although it's good at reclaiming the outline in general, it's pretty bad at the details. And so we might start to wonder, okay, well why would that be? And so after a bit of thinking, I think, oh, okay, well, it might depend on the value of this beta that we're using in the auto-logistic model, right? Because if that indicates very strong correlation, then that might kind of knock off the details at the edge of the cat, right? Because if we're in, say, a region here, then we might be kind of overwhelmed by the brighter pixels around us, and we'll lose that detail. And so you can start to kind of play around with this and see for yourself sort of different values of beta and what they give. So maybe I'll just try another one here, but I'm not going to run it as long. So maybe we'll just do 100 iterations. So we'll do a value of beta equal to 3, and let's try that. Oops. Again, we start quite noisy and we start to converge pretty quickly then on the true values. It's quite therapeutic actually watching this thing. We we used to have a neighbour downstairs that was a cat, and we used to, it was actually a Persian cat, it looked very like this, so that's what inspired this example. And we used to, so every day his owners would let him out. His name was Tor, and we would he'd start meowing, and we'd go to the window and we'd be waving down at him like Egypt's going meow meow meow, oh, you know. And so he'd be all about us and trying to kind of claw up the window and all the rest to get up to us. And then he used to sit in the window at the front, so when we went downstairs, we'd be leaving the apartment, we'd see him, and he'd sort of, if he was at the window, you'd knock on the window lightly and he'd kind of look at you and then just turn his head away. All about us 1 minute and didn't want to know us the next. Okay, so this is done, and now we could just look at the estimated image for that, and we can see, well, maybe we do a wee bit better on the details here. But we still don't have that sharpness. And so what I'm going to leave it for yourself to do is just kind of maybe play around with this a little bit and see kind of what you discover yourself, right? So different values of beta, and maybe try different values of theta as well. So even what you could do is you could generate the noise using one value of theta, and then try and recover the image using another, and see what happens. See the kind of the importance of knowing what those values are. So this code is up on Blackboard now, and so I think that's a good place to kind of wrap up for today.